So far, we discussed about the data collection and the type of analysis we might experience in quantitative analysis. So we discussed about the survey methods and the tools that we use for quantitative data collection. And today's lecture is about an introduction to quantitative analysis, right? What would you experience when you are doing quantitative analysis? So I have put this slide set in this order. You have descriptive statistics, outliers, and then stem and leaf diagrams, histograms, skewness and shape, bar charts, pie charts, categorical data of two variables, comparing two samples, paired data, and correlation coefficient. So what you would notice throughout this lecture is that I'm not going into the deeper concepts of mathematics because this is like the surface that we want. But when we want to understand the scope, we need to make sure that we look at the entire thing with the boundaries, so that when we dive deeper, we have a better understanding of each of these things in the next lecture or the coming lectures. So I'll start with descriptive statistics. So when I click on this now, if you want to look at the lecture series as a whole, you can click on this slide overview O button, right? When you press O, you would be able to see, like when you press O, you can see this slide overview like that, okay? Right, now I will go ahead with the descriptive statistics, the first slide. Now, when we collect data, particularly numerical data, we have observations. So we have sample observations like x1, x2, x3, so and so. So what is x1, x2, xn, these observations? They can be numbers about maybe the observations like number of birds, number of elephants, number of ice creams, number of participants, can be anything. So that's a numerical value. Whatever it is a numerical value. Now, once we get these data, the next thing that we do is trying to summarize them. So the first thing that we do as a summary is getting the sample mean, the average of all observations. Now, we from I think school days, we know what is a mean. So what we do is we collect all the observations and we sum them up. We sum up all the values and divide by n. So this is a simple n. Now I have given this n as the number of observations, right? We have some deeper discussions about whether this is going to be n minus 1 or n or what this value is. But let's keep them for a different discussion later. Today, we will be looking at all the concepts, like understanding all the names. Now, if you want to talk about cars, for example, we need to look at vans, cars, motorbikes, tricycles, tree shows, everything, and then try to understand what they are and then come back at each one of them later. So today, what we are trying to do is to get this concept going, and then we'll go into the details of what they actually mean in the coming lectures. So for today, we will take them, we sum them up, we divide by n. So if you think about what you do every day, this is what mean is about. So if I ask you, what is your average expenditure per day? What you do is you sum the days, the expenditure of each day, right? Monday, Sunday, Tuesday, all these things, and then divide by the total number of days, and you get an average. So the sample mean is the average of all observations. We know about this. The next one is the sample median. Sample median is the value of the middle of the ordered data set, which is positioned at n plus 1 divided by 2, which means now if you have a value set, what you do is you order them from the smallest point to the largest point. So we have the ascending order. And what we look at is the point at which we can divide the data set into equal portions. So that is where the median exists. That's why we have n plus 1 divided by 2. If n is an odd number, think about an odd number. Think about the fingers of your hand. You have 5 fingers, hopefully, right? So some people have 6 fingers. Apologies if I am referring to them, but I think most of us have 5 fingers on our hand. So if you think about it, the middle finger is the point. If you press that, you can see 2 fingers to the right hand side and the left hand side from your middle finger. So your middle finger is that median point. Okay. I'm not saying that it is the correct median, but I'm giving you the intuition about what is median. In the median, what we do is once we order them, right? Now think about your fingers without your thumb. Now, I believe they are in ascending order. If you start from your pinky finger and it goes to up towards up like with your middle finger, but there's another finger like index finger. Imagine that they are in order. Now you have 4 fingers, and in order to put them into 2 separate sides, 2 separate bins from the center, you need another value. So that's why we have n plus 1 divided by 2. So if you think about 4 fingers, 4 plus 1 is 5. 5 divided by 2, that is 2.5, right? So the mid value is between the second finger and the third finger. So that's why you add the 2 and then divide. The average of the 2 adjacent values. Now, that is median. And what is the purpose of median? Well, when you think about median, it has a lot of very interesting use cases. Now, think about a triangle. Now, in the case of a triangle, you would have a triangle like this, right? The values are ordered. Now, if you think about a triangle, they are in the ascending order. The height increases like that, right? Now, if you think about the middle of this triangle, based on the heights, so you can understand that this and this height, 0 and this, right? These are the heights, and the mid value would be somewhere in the middle. Now, if you think about this value and the value here, now they are ordered like from 1, 2, 3, 4, 5, 6, this order, and say 6 values are there. Then 6 plus 1 is 7. 7 we divide by 2, 3.5. Third value and the fourth value. In between that, you get the mid value, the median value. So that's the idea of the median. Now, let's look at the other one, that is the sample mode. The sample mode is the most frequent value. Now, what do you mean by the frequent value? Frequent value is the value that you keep seeing in the data. For group data, midpoint are the most frequent class when you are having group values. We'll discuss about it in the later sections. Now, in general terms, the idea of the most frequent value is the value that you observe in a data set. If you look at the data set, you keep on seeing this value. If you think about like your everyday expenses, the single expense that you do for a given transaction, and you organize them in a piece of paper and then see what is your frequent value. Sometimes you might be seeing 500 rupees or 750. Or if you are traveling by bus, for example, if you are traveling from Colombo to Katubed, for example, by an AC bus, I went in an AC bus, and I got to know that the ticket price is 200 rupees. So if I usually come to the university, and let's say I spend in between, perhaps because of my travel, if I look at the overall picture, I might see 200 appearing in my records because I frequently travel from Colombo to Katubed. So those are the ideas about the mood. So if there's a player who gets out, for example, for duck 0 in cricket, so the frequency of that value will indicate who is scoring less or who is getting out for 0, and so and so. That's the idea of sample mode. And let's look at this example. frequency table for 40 rolls of dice. So what is a frequency table? Frequency table is the value that you observe. This is the value and the frequency in front of it. So you have two columns and you have a value and the observed frequency. So the idea here is you roll a die. So we have a six-sided die and each side has an equal probability. We'll talk about probability later, but we know from our childhood that you have six sides and each side has a value. And because of that, we can only see from 1 to 6 values. But when you throw this die for 40 times, that's what 40 rolls mean, and then observe the frequencies, you tend to see 9 value of 1, 8 times the value of 2, and so and so. That is what the frequency is. Now, when you look at the frequency, the sample mean of this distribution or the mean that you expect would be 9 times 1, 8 times 2, 5 times 3, and so divide by the total number 40, 3.05. Because if you were to organize this set of values, there are 40 values. You have 9 ones. If we are going to organize them in the ascending order, the first 9 spaces would be taken by value 1. Then the second 8 spaces would be taken by value 2, and so and so. So you have 40 values at the end. Because of that, we are multiplying by the frequency. So that's why in the equation, it is xi times fxi. Xi is the value that you observe. Fxi is the frequency. So you add them up together, and at the end, you get the sample mean. Now, sample median is the average of the 20th and 21st values. Because you have 40 rolls of die, the 40 plus 1 is 41, and divide by 2, we get 20.5. Because of that, it's the median value between 20th and 21st value that add them up and the average. Sample mode is the highest frequency. So number 1 is appearing 9 times here. And because of that, it is the frequency. It's the sample mode. The mode is 1. Now, there are other values also describing the sample, describing your collected data set. The previous values, we call them the measure of central tendency or the center of the data. Here we have mean and median. They are the central tendency data. It talks about the center of your data. The measures of variability talks about the spread of your data. The sample range is the largest value minus the smallest value, which indicates the range of values that you observe. Of course, when I talk about this, you might get the feeling like if I have an anomaly, like if I get a very small value and a very large value, my sample range would be affected by this, right? So we have ways in which we can calculate this, whether this is an anomaly or not. From there, we have a different way to look at the sample, the actual sample range. But in theory, the sample range, the raw sample range that we observe is the difference between the largest value and the smallest value. Then we have something called sample interquartile range. So as I said, this particular lecture is about introducing you to some concepts in statistics, some ideas about the quantitative statistics. So sample IQR is the upper quartile and the lower quartile, the difference between that. So what is the quartile? Quartile is, remember, the median. In the case of median, I will refer to 5 numbers that we discussed. Say the values look like this, right? These are 5 values. The height indicates the value. So they are ordered in the ascending order. Now, the median of this value, the median of this sample would be this one, because the mid value, which equally divides the set into 2, right? Now, the quartile is the quartile indicates. Now, here what we do is we divide the sample into 2 equal sections. The number of items in the divided sections would be equal, 2 equal. In the case of quartiles, what we do is we do it for 1/4 of it. So the first quartile is the point which divides the data into the 1/4 of its total, right? And the remaining would be there of 3/4. So we take the remaining part, this part, and then divide it again, and so on. So at the end, each quartile will have 1/4 of data values of that distribution or the sample. So that is the idea of a quartile. And the upper quartile is the third quartile, and the lower quartile is the first quartile, and the difference between these two is considered as the interquartile range. So that is what the IQR means. Now we'll come to that in few slides. What is sample variance? In the case of sample variance, now notice that we have divided by n minus 1. So whenever we refer to the sample, please divide it by n minus 1. At this point, we should not discuss why we are dividing it by n minus 1, because we will be diverting from our original discussion. We have a lot to discuss. So n minus 1 is the general way of calculating the sample variance, which is the correct way. I'll talk about this if we get the time, but there's a difference between dividing by n and dividing by n minus 1. For the mean, you will be dividing by n. For the sample variance, you'll be dividing by n minus 1. The easier way to remember this is, in the case of sample variance, you will notice that you are calculating two things. The first thing is you first calculate the mean of the sample, x bar, dividing by n. And then you again use the sample values to calculate the variance, xi. When you want to get the sample variance, what you do is first you calculate the mean, and from each observation, xi, you reduce that mean and square that value. And then the summation of all those values divided by n minus 1 will give you the sample variance. So in simple terms, you can remember, just because we are doing the calculation twice, that's why we are dividing by n minus 1. Think about it like that if you forget. So when you want to calculate the sample variance, you are dividing by n minus 1 for the sample. Now, sample standard deviation is the square root of this, right? So we first of all calculate the sample variance and then get the square root of that. So what does sample variance actually give you? Sample variance is very simple if you understand it like this. Now let's look at our simple example of 5 numbers. Let's say 1, 2, 3, 4, and 5. So these are our 5 numbers. And the mean of this is, we have 1, 2, 3, 4, 5 numbers. So n is 5. The mean of this one is 1 plus 2, 3, 3 plus 3, 6, 6 plus 4, 10, 10 plus 5, 15, 15 divided by 5, that is going to be 3, right? So this is our mean, or in other words, x bar. Now what do we do? So this is our 3. If you think about the number line, let's look at our number line. This is our number line, sorry, this is our number line. So you have 1, 2, 3, 4, and 5. Now our mean is 3. So this is our mean. Now we have calculated x bar, and now we need to calculate the sample variance. When we want to calculate sample variance, what we do is we start with our first value. So our first value is 1. 1 minus 3, that is going to give us negative 2. Okay, I will write down them in the green color here, negative 2. 2 minus 3 is going to be minus 1. 3 minus 3, that's going to be 0. 4 minus 3 is going to be 1. 5 minus 3 is going to be 2 again. Now you can see we have identified, for this particular sample, it's easy to see that your mean is 0, and you have to the left hand side and to the right hand side some value variation. Now, because we are getting negative values, we are squaring them up to make them positive. So when we square them up, we get 4, 1, and 1 and 4 again, right? So what we do with this is, if you draw a line like this, we have how spreaded the values are, right? We have some idea about the spread of this value, like that. So when we calculate the sample variance, we are getting, in simple terms, don't get me like as factual, but I'm giving you the intuition. We are getting something like of the spread of this entire thing, right? The spread of this entire thing. Because of that, it's a square value, the variance. But when we are calculating the standard deviation, what we do is, if you think about a square matrix like that, what we do is we are getting the square root of that to identify that little width of it. So the sample standard deviation would give you that one measure of the variability of the spread. So that's what standard deviation means. In that case, we are simply taking the square root of the variance. Okay, now let's go ahead with our remaining slides. So I have given you a computational formula for variance, and because of a typo, this is wrong. There are no boxes here. It's basically the square root of this entire thing. And why have I given you this computational formula for variance? It's because when we are calculating this, right, by hand, even by computers, we can have a lot of errors because we have to calculate x bar, we have to calculate the difference, we have to get the square, so and so. So to avoid that, we have calculated this particular formula where if you have the x bar, simply the square of x bar times n would be enough, and you have the sigma xi square, this one, where what you need to do is, if you have xi observations, 1, 2, 3, 4, so and so, you can have a column where you have the xi square. So xi square is there, and you get the square of all these values, and adding them up at the bottom would give you sigma xi square. And what you need to do is minus n is the number of observations, and x bar square is the value that you calculate. It's a constant because x bar is calculated, it's the mean. And by getting this and dividing that by n minus 1, you can get the s, where you minimize the number of calculations. It's easy, right, when you are doing it by hand. Right, let's go forward. So that's the standard deviation. Right. Now there is an interesting thing. It's about population. So far, in the previous cases, we talked about the mean in the sample, variance in the sample, and the standard deviation. So in all these cases, I referred to the total number as simple n. But when we are dealing with the population of interest, we have to divide it by capital N. Usually, this capital N is unknown to us. We don't know, right? This is unknown. This is very important. This one is unknown to us. So that's why this whole idea of sampling, inference, confidence intervals, and all these things come because of that. Because population is unknown to us, the number of things in the population. Even this mean mu is unknown to us because we don't know the total number there, because we don't have the observation of all. We don't have the observations of all. Because of that, we don't know about mu. Because of that, we don't know about sigma. We don't know about capital N. So everything is like abstract. Population mean, population variance, population standard deviation, all of these things are guesses. In very simple form, they are guesses. But we have some mathematical educated guesses on that. So remember the notation. So when you are reading a research paper, if you see mu, they are referring to the population. If you see capital N, unless otherwise specified, they are referring to the total number of the population, and xi is the observation. Sigma is the standard deviation, and mu and sigma are used for the inference. So when you're reading a research paper or a textbook, remember this notation clearly. Right. Now, I have given you some example of cotton content in fabric. So there's a manufacturer who claims the fabric is 80% cotton. The fabric is 80% cotton. So measurements from two balls. As I said, we cannot go into the manufacturer's entire stock and then get all the all the fabric and then sample it. It will be very expensive plus unrealistic. So we need to find out this whether this claim is correct. So what we do, we have 20 samples, so 20 measurements, 20 samples from the fabric, and these are the values, the cotton percentages from each of them. So we have 20 of them. And the sample mean is what we usually do. We add them up and divide by the total, and we get the sample mean. And the range is also straightforward. Sample variance is calculated by n minus 1, dividing by n minus 1. Remember our calculation. And the standard deviation is also calculated. I'm not talking about anything at this moment, but this is very basic understanding of the basics of mean, range, variance, and sample standard deviation. Now let's look at something more than that, something further to that. I talked about the quartile in the previous discussion. The median divides data into two equal halves. Quartiles divide ordered data into four equal parts. So think about this is like a grade 5 scholarship question. How many poles can you put between two ends so that the space is divided into four? So the grade 5 scholarship examination question would be, you have a land like this, right? You need to divide this land in and put poles so that you need to put poles so that you will have four, sorry, you have four, where is this? Okay, you have four equal parts. So this is the grade 5 question. So in order to have four equal parts, what do you need? You need three poles, right? Because three poles, if you put them like that, we'll divide it into 1, 2, 3, 4 parts, four equal parts. So that's the idea. So we are talking about quartiles. It involves four, but we only have three measures. Remember that. Okay. We are talking about quartiles, but we only have three measures. There is no Q4. What we have is the minimum value of the data set, and then the maximum value of the data set. Those two are there. They are inherently with the data, minimum and the maximum. Q1, Q2, Q3 are the values that we calculate. 25th percentile is the first one, 50th percentile is the second one, 75th is the third one. So we have three quartile values, and each of them dictates how the data set is separated into equal four portions, right? Now, with that, when you have this thing, we have five values. Minimum of the data set, Q1, Q2, Q3, and the maximum of the data set. Those five values are called five number. Because they are numerical summaries, we call them five number summary. Okay. So whenever someone refer to five number summary, they are referring to this minimum, maximum, and the interquartile values, the quartiles Q1, Q2, and Q3. Remember that. Okay. So let's go forward. So I have given you an example calculation for the same cotton data, the first quartile, second quartile, and third quartile, and what are the values, and five number summary of each one of them, 75, 76.5, and so and so. So you have the minimum Q1, Q2, Q3, and the maximum. The interquartile range is the difference between that third pole and the first pole, Q3 minus Q1, the difference between them, and we get a value. This is IQR. Okay, now when I take you further, you will notice some interesting thing that you have seen in research papers sometimes. So that is called that 100 percentile is something that we know, right? You divide the values into 100 equal parts, like you do it with the QR, Q1, Q2, Q3, and then you get the percentage. But that's not what I'm referring to. I'm referring to this, the box plot. So when you see research papers like in chemical engineering or civil engineering or any quantitative method papers, you might see medical papers, you might see a box plot, something like this. So how do we draw this box plot? The box plot is drawn using the first one is the minimum value, and then you have the maximum value. So these are called whiskers because they put the demarcation, the boundary for your data. Then you have the first other boundary, that is the Q1, the smallest one from the Q family, Q1, and then you have Q2, which is the median or second quartile. And then you have the third quartile here, right? The box itself is the decoration. So these values indicate that spread. The box, the width of the box is Q3 minus Q1. That is the interquartile range. So whenever you see a box plot, the box plot contains a lot of information about the spread of that data. Sometimes when you are looking at a line chart, you might see this box plot attached to each observation. It's not, in fact, when you are seeing that, it's not a single observation. Like for example, if you see a line chart like this, so imagine that you see a chart like this, and this is a line graph like that. But in this line graph, you might be seeing a box plot like that. For each observation, you might be seeing a box plot like that. I'm sure you have seen these type of papers in your literature review. So when you see this doesn't mean that it's a single value. It's basically indicating that for that particular observation, they have done multiple values, they have observed multiple values, and this is the spread of that value, right? With the box plot, they are showing that. And the line graph may be drawn maybe from their mean or the median value. The line graph may be connecting the median values or the mean value sometimes. So you have to understand how those charts are developed. That's because they will give you a clear idea about the value. So box with IQR, box contains the middle 50% of the data because Q3 minus Q1 indicate the first 50% of the middle part of the 50% of your entire data set, right? And the whiskers extend to the smallest to the largest non-outlier observations. Now, when I say non-outlier observations, inherently, right? Inherently, we get an idea of, so if I say non-outlier observations, so how do we calculate outlier? How do we get this demarcation, right? How do we say it's an outlier? How do we say that this particular value does not belong to our observations, does not belong to our analysis? This is a very critical question. So how do we do that? When you do that, we have a technique to calculate outliers. So getting outliers from a distribution, it's still an ongoing debate. You might find a lot of techniques, a lot of interesting philosophical discussions, right? But one of the most established ways is getting this 1.5 IQR. So you first calculate the interquartile range from the data set, Q3 minus Q1. This is the interquartile range. It is a value because the difference will give you the span between Q3 and Q1. 1.5 of that will give you the nearest quartile as an outlier. If further than 3 times of that, right, that is an extreme outlier. So this is how we calculate the outliers and extreme outliers. So for your observations, for your data collection also, if you get values and we draw a box plot, you calculate the 5-number summary, we get the interquartile range and multiply by 1.5, the value to the right-hand side, to the left-hand side, that is an outlier beyond that. But if it is beyond 3 times of IQR, it's an extreme outlier. whiskers extend only to the smallest or largest non-outlier values. So even though in the previous case, we have drawn the whiskers to the smallest and the largest values, those two vertical lines, when we calculate the outliers, when we do it, when you are doing it professionally, we first calculate the outliers and then draw the whiskers accordingly for the non-outlier values. Outliers are plotted as individual points. So you might see an example here. So you have whiskers extend to smallest data point within 1.5 interquartile range. So it's the first quartile here. So this is the interquartile range. You can see it starts from, so this is the interquartile range, right? 1.5 times of that. You can even look at it from the screen as well. Let's do a fun thing. We'll try to see whether the actual size is there. So this is the size of the interquartile range. Let me check whether I can move it. So this is the interquartile range. So this is the interquartile range, right? And one of interquartile range. So I'm going to draw another half of the interquartile range like that. So let's assume this is half of the interquartile range, okay? This may be the half. And now I'm going to now I'm going to take it. I want to move it. Move it. So how do I move it out? And now I'm going to put it there. Excellent. So otherwise my credibility will be also questioned. Now here, 1.5 times the IQR. Forget about these small things, okay? But in all honesty, this is correct. So 1.5 IQR to this side. So you take the first quartile minus that would be the first starting point of these outliers, right? So anything inside anything inside 1.5 IQR here is considered to be okay. It's there. And here also plus 1.5 IQR, anything inside that is considered to be okay. So they are considered non-outliers. But anything beyond 1.5 IQR is an outlier. So here you have outliers, here you have outliers. And anything beyond 3 times of that is an extreme outlier. As you can see, that's an extreme outlier. So whiskers extend the largest data point within 1.5 interquartile ranges from third quartile. So only up to the existing data point, right? This is the whisker, not the smallest and the largest value. So I hope that is clear. So just to check whether you are listening to me, can you put something so that I know you are here? Some thumbs up, or I hope everything is all right. Say, okay or something in the chat so I know you are listening. Okay, thanks. Now, we take from here to the next stage. So we have the interquartile range, and we have an idea about the interquartile range and what is an outlier. Let's move forward. Now, this is an outlier. So for the cotton data, we we do the same technique, we do the same thing and see what are the outliers. So it's just it's calculation. You can go and see the slides. And then, of course, we are trying to develop our intuition here. And when we talk about stem and leaf diagrams, they are not usually used nowadays. But anyway, we do that so that we can develop an idea about the things to observe in the future. So when you look at stem and leaf diagrams, stem and leaf diagram is basically, now when you look at a stem and leaf, stem is this in a leaf. So this is the leaf. Okay. So this is the stem and this is the leaf. So stem basically is the one or more leading digits, the digits in front of the number, that is the stem. Leaf is the remaining digits. So if you have like, let's say 100, we can have 1 as the stem, and then you have leaf values, anything above 100, say 125, then stem would be 1, leaf would be 25. So we are basically dividing the values. It's a very interesting thing which was used in the past. Now you don't necessarily need it in our novel data analysis tasks, but it's very interesting. So let's look at the example compressive strength of aluminum lithium alloy. Look at the values here. We have around 80. Not around, we have exactly 80 values. So let's calculate whether we have 80. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 1, 2, 3, 4, 5. 16 times 5 is 80. So we have 80 values here. And now what we are going to do is we are going to put them into stem and leaves. So we have to divide them into stem values and leaf values. When you do this, you have to be very careful how to choose your stem, because stem needs to be there. Okay. So if you choose, let's say if there are 200 values, and this one, for example, if you choose the stem to be 2 and the leaf to be 29, by all means, no problem. But you will be only plotting, or you'll be only using the values greater than 100, because when it comes to like values like 70, 80, where is 70, 76. So when we get 76, we cannot plot the stem and leaf diagram. So we look at the smallest significant numbers and then find the stem there, right? And then from there onwards, we develop the other. That's a practical way to do it. So when you do it, this is the stem and leaf diagram. So you have the stem from 7 to 24, and you have the leaf. The leaf values nicely indicating the available value set and the frequency of the value. So how many values are in the range from 250 to 159, have 10, so and so. So by looking at this, what do you get? By looking at the stem and leaf diagram, what can you get? As you see, what is your observation? With the stem and leaf diagram, what do you get? You can easily see the distribution, right? Because when you have these values ordered to the right hand side, when you tilt your head, you can see that normal kind of a distribution, like a bell curve, like a distribution. It's very, very, very nice, very nice. So you can see the distribution for your data. Give me a moment. So with this one, you can see the distribution of the data. Now let's go forward for the histograms. Now we have an idea about what the data distribution means in a data set. When we organize them in the stem and leaf diagram, we can see the distribution of the data. Now histogram is the tool that we use to do that. A frequency distribution tabulates frequencies and or relative frequencies by class interval. So forget about what the class intervals and all these things mean. What this frequency diagram means is that you have, like in the case of aluminum lithium alloy case, you have some values, right? And if you draw the values like that, if you start from 0 and then somewhere here you have the starting value, somewhere here you have the value separation. So if this is 150, and if this is 160, for example, values between that, how many values were there? So you draw one bar for that. And then for the next one, you draw another bar. So another bar like that. So you have that frequency, the number of times the value being observed, you draw that. So that's a frequency distribution. And we call this a histogram. The key steps is that it divides the data range into class intervals. So bins. In the previous case, the stem and leaf diagram basically shows you how many intervals were there. And then count the frequency in each bin. Relative frequency is the frequency divided by the total observations. The rule of thumb is that the number of bins should be the square root n of the observed value. So if you look at the number of observations, square root of that will indicate the number of bins that you need to keep in your visualization or in your analysis. So it is representative. A histogram is the visual display of the frequency distribution. So that's what a histogram is. So typically, when you are collecting data in your research, you will find values like this. Maybe a range. Let's say how frequently you do something, or what is the value that you observe, or how many cars you observe between this junction and the other junction, the distance between them, all these things. You have the frequency and the class. The class is that separation. And then the relative frequency is you have the total number of observations and the frequency for that. Then what you do is you divide that by the total number of the frequency and you get a relative frequency. The beauty of the relative frequency is that at the end of the day, the summation of these things add up to 1. So you can actually assume that this is a probability distribution because the values add up to 1. And we'll talk about it later, but that's the idea. So when you convert the frequency into relative frequency, you actually have something more to analyze about the data set. So this is the histogram of the aluminum lithium alloy example. So you have the frequency and the distribution, and you can nicely see the value. And if you remember the stem and leaf diagram, you can see that it's the same distribution, but here it's the other way around with a chart, right? And if you have unequal bin width, what you have to do is you have to get the bin frequency and divide by the bin width, so to get the rectangle height. Unequal bin width means this thing here. If you have differences in these bin widths, then in order to fix this height as the proper frequency, what you need to do is to get the bin frequency, the frequency of that, and then divide by the bin width, and then you set your frequency height. So that's what you do when you are developing a histogram. Right, and visual impressions of the shape and the distribution and information about central tendency, the mean, median, and the standard deviation, dispersion, and also suggest possible probability distributions. This is very important. This is one of the most important things about quantitative analysis because it suggests us the possible probability distribution so that when we go for inference or as you get your sample data, when you want to infer about the population, then you need to know the probability distribution in order to get those correct probability values. Like if you have heard of the z-score, for example, z-score, p-value, alpha value, those are calculated from the probability distributions. And the histograms allow us to understand to which distribution actually the values belong to. So that is a very important thing about drawing histograms. And let's talk about the skewness and the shape of the distribution. I'm sorry, I'm taking you very fast and along this one because I want to capture everything and try to make sure that the recording is available so you can revisit it. Skewness and the shape. So the symmetric bell-shaped, those are the distributions that we usually accompany our world. So this is the normal distribution, symmetric and bell-shaped. The shape is a bell and it is symmetric along an axis. You can fold it. If you fold this one, it's symmetric, equal from this side and equal from that side. The most common ideal shape is the symmetric bell shape. A data set not symmetric about its median is skewed. So whenever you observe a data set that doesn't have this property, maybe it goes like this, maybe it goes like this, then we call this skewed. Skewed. There is some wrong with the data set. That's what skewed means. So right positive skew means your mean is located towards the left-hand side and the median is somewhere here. So your mean is smaller value, median is a slightly higher value, and the mode is somewhere at the latter part, like the higher value. So we call it right skew. Okay, because your mode is observed like that. So your mean it's high. Sorry, left or the negative skew is long tail to the left. So you have a tail here and you have something like that. So your frequency, the mode is higher and mean is low. So this is the idea of that. So let's look at an example. So when you look at an example, this is right skewed data, and this is left skewed data. Okay? In the case of right skewed data, you would see high frequencies, right? High frequencies near the smaller values. High frequencies near the smaller values. Because of that, your median is at the center of your mean and more in center of your mean and mode. So when you think about the negative skew or the left skew, you can see high number of values, high values towards the high side of the distribution or the larger side of the value. So the, the height is towards that side. So left is your mean. So basically, we look at the if you want to remember it, if to our right hand side you see the tail in the right skewed, towards your left hand side you see the tail in your left skewed data sets. Okay, right. So let's go forward. And shape of distributions, when you read research papers, you would see that some people claim different things like you see bimodal, you see unimodal, you see multimodal, and you talk about multiple variables contributing to something. We talk about that there is a possible convergence to a value. Maybe you talk about two values that dictates a distribution, right? So all these things are related to the shape of the distribution. When you create the histogram, the unimodal data means it rises to a single peak, then declines. So you have one peak. Bimodal is two distinct peaks. So you can look at the shape and you instantly identify. There are two subpopulations because you have two distinct peaks. So when you actually look at the score, sometimes you look at the scores, for instance. If you look at the first year scores in engineering at University of Moratuwa, you sometimes see multimodal distribution. So you have more than two peaks. So there are three or more peaks because you have a certain segregation. That's what it says, subpopulations. We should see now, I'll show you the distributions. Now, this is a unimodal distribution. Look at this. In the unimodal distribution, the height, there's only a single peak, one peak here. In the case of bimodal data, you can clearly see two peaks, indicating there are two subpopulations. Two subpopulations in the sense you can clearly see that there are two classes of your data, right? Because you have two particular sets with high peaks, right? Two sets. In the multimodal case, you have multiple subpopulations. You have multiple classes, different classes indicating different heights. Now, when you look at University of Moratuwa first year, where they put them into different departments, you might see multimodal distribution based on the places they come from, their English language expertise or fluency in English, sometimes their mathematical abilities, and of course, the learning environment, how quickly they understand the concepts. You might see a multimodal distribution as well. Look at the marks distribution, right? In the case of like bimodal distribution, you clearly see high scoring class and a low scoring subclass. So you can see that as well. So that is what multimodal distributions and unimodal, multimodal, and bimodal distributions look like. So this is very basic bar charts, but it's very powerful. A bar chart is a histogram. Now we are looking at a histogram again. What are histograms? Histograms are charts, bar charts actually. Histograms indicate the height as the frequency, and then the X value or the bin value. The bin value is there indicating the class or a particular interval of values and the frequency of that. The height indicates the frequency. A bar chart is a histogram for categorical data. Categorical data. So categorical data, what are the categorical data? They can be nominal or ordinal. Nominal values or ordinal values. When you go and do a sampling survey, you have the preferences. Strongly agree, moderately agree, disagree. So you have some categories. For each category, you have the number of response. So that's a bar chart. For every response, you have this bar indicating how many people or how many respondents have given strongly agree, disagree, or so and so. Each category has a bar whose length is proportional to its frequency. Bars can be displayed vertically or horizontally. Gaps between bars, unlike histograms. Now remember, in the case of histograms, we are looking at continuous data. So continuous data cannot have gaps. They have to be drawn like that, even though when you're charting, when you're doing the charts, you get these gaps. But gaps between bars signal category in this bar chart, not continuous data. So let's look at this example. An engineer tracked machine breakdown causes over 1 year. There are 46 total cases, like your survey data. So you have breakdown cause is electrical, frequency is 9. It's a mechanical cause, so you have 24, and misuse 13. So this is the data set that you get. Now, when you want to observe this and you draw a bar chart, you can see it nicely. And if you have more and more data sets, you can see the spread of the data. Which one has more casualties? Which one has more frequency? And always remember, the truncated axis can give you wrong impression. So when you're developing thesis, for example, don't do this one, right? If you want to actually show something like this, for example, if you really want to show something like that, the best way to do it is you first draw a small chart like this of your actual data set, and then maybe take a subclass to indicate this in detail so that the reviewers or the readers would be able to read it clearly. But don't put this one as is, it is exaggerating what you actually try to show. So always check the frequency axis. A truncated axis creates misleading visuals and impressions because this is very small variation. You have like 89, some other value near 87, 85 or something, and then 100. So it's very small deviation, but if you look at this one, entire thing is looking like that. If you want to clearly show it, you can just highlight it and then take it as a separate visual, as a part of it, but not individually showing it like this. Right. Let's go forward. So pie charts. Nowadays, we are not advising students to draw pie charts because pie charts can be misleading in terms of visualizations because the categorization is not clear. You can see they are very small, so you can't really see the value, but this is something that we know from our grade 10, so we'll skip through. Categorical data of two variables. Now, in research, now we are talking about research, right? We are doing this for the research. So when we do that, we have more than one variable, obviously. In a thesis, in a PhD thesis, you may have 10 variables, 20 variables. In an MPhil work, you might have 5, 6, 7 variables. So we have more variables. And in the case of categorical data of two variables, like in this case, machine breakdowns by shift, you have a contingency table. In the contingency table, you have the machine, the label of the machine, and the number of items, maybe the machine breakdowns, right? For each shift. So if you look at just one line of this, the first row of it, it indicates the machine failure for the shift 1. Then you have shift 2 and so. So when in the distribution, you can see 1, 2, 3 as clustered distributions, and then you can see separately. Now, what is the importance of this when you're analyzing quantitative data? Because from the visual itself, you can understand what sort of failures might be high for each shift. Now, look at this. Shift 1 and shift 2 has higher number of reported machine failures. The yellow color bar is high here. But if you look at the shift number 3, you can see machine B, the orange color bar, has a slightly higher value than the yellow color one, which indicates there are more failures in the machine B in the shift 3. So these are the things that you can capture from data from when you have multiple values. If you put cluster bar charts, comparing two samples is a very important thing that we experience when we are doing research. So let's look at this. Now, I give you some time to look at this value. So it talks about the lead concentration. It's from a real study. Okay, this is from a real study, and it contains lead concentration. Lead is obvious, it's a heavy metal, not a good chemical for us, for humans. So you have lead concentrations. In 1976, in near a freeway, so it's like a road, not like a road, it's a road, so it's a freeway, and not a highway. So like a normal road that we have in front of our houses or in front of the school, university. So that's a freeway. And you can see the concentrations, micrograms per cubic meter. And these are the values in fall 1976. Fall is in US, fall is like like November, like the tree leaves are falling, right? That's the fall. Or the rain is there, like we are ready for the winter, something like that. So 1977, you have higher number of or whatever the values. Now, we don't know whether it's high value or low value. We just capture near the freeway the concentrations of lead concentrations, right? So you capture these values. Now, let's look at what we get. So we get in 1976, the mean is 7.291, then standard deviation is this. And we get a similar standard deviation very close to that in 1977 as well, but we have a higher mean. So when we draw a box plot, so this is a box plot, remember? When we draw two box plots for 1976 and 1977, we clearly see the difference between the median values. And at the same time, you can see the outliers. You can see clearly there are outliers in 1977. So there may be high concentrations and low concentrations of lead in your measurements. So both summary statistics and box plots suggest lead concentration is higher than 1976, of course, but of course there are anomalies here as well. So we have to look at where do we see increase in lead and decrease in lead. So that's what the comparison of box plots indicate. Right, let's go forward. Paired data scatter plots. So we talk about correlation coefficients. We will talk about them in the coming lectures. So to get these things, we have to draw scatter plots, right? So you will be able to make a scatter plot to examine a relationship between two variables, to describe the overall pattern and any striking deviations, describe form, direction, strength of a relationship, identify outliers using scatter plot, and then why we need transformations, data transformations. Let's look at this. Now we are getting a bit complex in our data analysis. So imagine that we got a study like this, laundry detergent study, 53 detergents rated 1 to 100. So think that you have done a study. So I have 53 detergents and there's a rating 1 to 100, a rating value on washing performance, and also the price is given. So how many rupees you spend per load? 5 to 60 rupees. Of course, now I think the price value should be higher, but let's look at the value, the only the research part of this. So you have price and the rating. So explanatory variable, we call these things explanatory variable because this is the independent, or this one explain. We are trying to develop an explanation about what we observe from this value. So price is the explanatory variable. Response variable is the rating. So the rating is what we get as a response. So we expect higher price detergents to have higher rating. So this is your hypothesis. So you expect higher values or higher price detergents will give us higher ratings. That's the idea of this. Let's go forward and see what we get. So in the laundry detergents, we will look at the plot. One detergent rating 85, price 50 stands out as an outlier. So you look at the values, you can see 50 rupees, 85, and this is an outlier. Okay. So this is an outlier. How we get this, how we do this, it's a different discussion. but this is how you look at the data. So you plot them and you fit a line, linear line, linear regression. So always plot the explanatory variable on the x-axis. So this is our explanatory variable. This is our response, and you put them, and then we fit a line. And this one is, we find that this is an outlier. And you can see 50 rupees, but rating has very high rating. Now let's go forward and see some other things about this. And substantial variation in ratings of products priced at 14 rupees per load. No further outliers, examine the trend line. So we remove that outlier, and now when we remove that outlier, we can clearly see that increasing price per load does not necessarily result in the rating, increase in rating, right? So that's something we identify from the scatter plot. There are many things that we can talk about in a regression and regression. No, we can talk about it, but in very simple way, when we plot it, we can understand the scatter plot is giving us this, it's revealing this information that higher prices does not necessarily go for higher ratings, right? So you can easily understand it from the plot. Now let's look at the other one, positive and negative association. Positive association, above average values of X accompany above average values of Y. So advertising spend versus sales. Negative association, above average values of X accompany below average values of Y. So what this in words says is, let's look at this, for example, state spending versus population. So you spend, these are states, US states, and spending is there, and then the population is there. And let's look at the charts. A benchmark comparing process of one organization and civil organizations. A scatter plot of education spending versus population. So the strong positive relationship. Let's see. So this is the spending. Population is there. State spending is there. And then when you draw it of state spending versus population, so this is state education spending versus population. And now you can see box plot of state spending and scatter plot versus population with trend line, and you can see the distribution deviation from which states are deviating from the expectation. So the natural expected, or rather the expectations that we get from the data. Now let's look at something interesting about numerical values. So when we plot numerical values, if you look at this particular data set, you have the calcium intake and the retention, milligrams per deciliter or decimeter, or milligrams for some measurement, some volume measurement, right? So calcium intake and the retention. This is in human body. These are real results. Okay, I'm not forging anything. These are real results. Now let's look at this. When we plot it in a scatter plot like this, so these are numerical data, quantitative data, we get them and we plot them. Calcium, the y-axis, calcium retention, and then x-axis is calcium intake. So these are the values. When you plot them, right, there seem to be a linear relationship somewhat like this, like very small one, very faint, something like that. But it's very difficult to say, right? Now let's go forward. So the relationship between calcium intake and retention is not linear. It initially rises, then levels off. Let's look at this. So somebody can argue it goes like this as well. Okay, that's what it says. Now let's go forward. Now it initially rises and then levels off. Now data transformation, like log transformation, can linearize curve relationships. Replacing original values with transformed values is common in statistics. So if you are learning machine learning, if you want machine learning or data science or deep learning, machine learning things in your research, we always have to do this transformation, because we can't just take values and put them into models, because they are not necessarily giving us that model. So the use of a transformation is an art requiring judgment. So don't go and talk to your supervisor and ask him or her about which transformation is more suitable, because if if he or she doesn't know much about your data set, if they don't have experience on what you are doing, your data set, it's very difficult to tell what is the correct transformation. It's up to you to decide. You have to do it. Okay, so you have to do the transformation and see that. Now let's look at the transformation. Now log calcium intake. Now in this case, we get the log value of the calcium intake, and then let's see the retention is the same, and then let's see what we get. And let me delete these values, clear my drawings. Now you can see some other pattern. Now you can see some clear variation. Now, even though there are some clustering as well, some linear relationship can be fitted. After applying log 10 to intake, you get this. Right. Applying log 10 to retention, you get another one. So here y-axis get the log 10. So yes, log of the y-axis, x-axis has the values, normal values. Previously, x-axis log, y-axis no log. Here x-axis no log, y-axis log. And that initially what you get here is that when you do a transformation, I don't want to discuss in detail about these transformations here, but when you do a transformation, sometimes they reveal more details, or they can be modeled with more certainty with a transformation. So remember that numerical data, when you collect them, they have to be treated with scrutiny. You have to look at the data, you have to look at the outliers, you have to plot them to understand the distribution, you have to look at the relationships, and if they are not in the line that you expect as a researcher, then you might have to do the transformation and see how close these things can be modeled to some certainty. Right? Now let's look at what is correlation coefficient. So this is the equation for the correlation coefficient. What it does is, I will explain what it does so that you can develop an intuition of what it does. So remember our previous example about what the xi minus x bar does to you. So this is your xi. So I'll draw it in a clean way. So look at this, and I will draw as cleanly as possible. So this is your chart. Ignore this top and the bottom, okay? So this is your chart. Now, x-axis is here. So imagine that your x bar is here. This is your x bar. And this is your y bar. Somewhere here you get your y bar. Okay. Now, x bar and y bar. Xi observations. Now, if you take a look at one observation, let's look at one observation like this. So this is an observation. And this is xi, yi. If you take a look at your value, it indicates an observation xi of explanatory variable and yi of your response variable. And when you take xi minus x bar, okay, so this is, I will draw it in blue. So this is your x bar value. So this is your x bar value, and this is your y bar value. Okay, I'll try to draw it in yellow. So this is your y bar value. So when you get xi minus x bar, okay, when you get xi minus x bar, you are getting this value, xi minus x bar. When you get yi minus y bar, you are getting this value. Okay, these are the two values. And when you get sx, so sx, don't read it as a dirty word, it's sx. Sx is the standard deviation of the x values. So remember, we are treating them as separate things. So sx indicate the standard deviation of the x values. Okay, remember I talked about the dispersion of the values in the variance. So sx is the square root of that variance. It's basically telling us how spreaded are the x values. Let's take a look, take them, and this is the spread of x values. Let's say this is the scale of the spread. And in terms of the y values also, SY indicate how spread are the Y values. Let's say this is the scale or the length of the spread of Y values. So when we take this ratio, this one and this one, what we do is we take the ratio between that particular observation here and its distance to the X bar and the Y bar as a proportionate value to these two, right? We get the summation of it. So at the end, we get a ratio kind of a value. That is what correlation coefficient is. And in simple terms, at the end, we get the XY correlation, okay, divided by Sx Sy. So this is the sample correlation coefficient. It measures the strength of a linear relationship. Okay. So if the value is closer to 1, if the Sxy is equal to Sx times Sy, we get an idea that increasing X result in a similar increase in Y. So that's why when R is equal to 1, we can say that our relationship is pretty much accurate. The correlation coefficient indicates that correlation strength is high for those values. So that's why if it is closer to 1, we say that the strength is there. So Sxy is the sample covariance. Covariance measures how pairs of values covary. How they behave as a pair. However, its magnitude depends on the units of X and Y, making direct interpretation difficult. So when you get some R value, look at your units, try to normalize them, try to remove the units and make them unitless. Correlation divides the covariance by x times xy, making unit free and bounded between -1 and +1. So these are some of the correlations that you get. Okay, correlation R equals 0, a spread of values. It doesn't mean that they don't necessarily interact, or one does not cause the other, and so and so. Basically, we are looking at the statistical linear relationship. So correlation R -3 looks like that. Correlation R positive 0.5 looks like this, and so and so. So this is correlation negative 0.99, positive 0.9. So look, you can see as we change that correlation value, how close the values get to a linear relationship. So R equals +1 is perfect positive linear relationship. -1 perfect negative. Anything positive is positively correlated. Anything negative is negatively correlated. Correlation does not necessarily imply causation. R means association, not causation. So as I shown you, it's basically giving us that ratio between that variation of X and Y. It doesn't necessarily mean whether X is causing Y. Okay, you need more analysis and more parallel analysis of other things to talk about causation. But basically, most of our statistical analysis are about correlation. So real world examples of R, positive R, advertising expenditure is increasing revenue, sales revenue. Temperature increase is we are giving more ice cream sales because more of the heat results in more ice cream sales. Increase in height is generally increase in weight. Okay. Increasing in education years is supposed to be giving you more income. I'm not sure about that, but it's positive as per, looking at the qualifications nowadays, but it's very difficult to say whether it's true or not. Okay. Negative unemployment rate increasing means consumer spending is going to be less because people don't have money to spend. Vehicle weight increase, fuel efficiency is going to go down because when the weight of the vehicle is high, you need more energy to drive the vehicle. So your fuel efficiency goes down. So strong R ±1, height versus weight, medical data, years of education versus income level, near zero, shoe size versus IQ. So it doesn't mean whether you can't say whether your feet are large or small, whether that is contributing to IQ. Hair color versus music preference. It's very difficult. I mean, there is no statistical significance. So Important consideration for correlation: no directionality. R does not distinguish explanatory from response variable. It doesn't do that. So it doesn't understand which one is explanatory, which one is response. It doesn't understand that. Remember that whenever you come up with R, you know, when you say R doesn't know what is explanatory variable, what is response variable. Quantitative only, both variables must be quantitative. Unit invariant, changing measurements units does not affect R, because you remember SXY divided by SXXSY. So the units cancel out. Outlier sensitive, R is not resistant to outliers. R is not resistant to outliers, which means when you have outliers, you can get different R values. So when you read the research paper, look at how they have reported it. Not all research papers are equal. Not all of them actually report correct results. They might be manipulating. Look at the research paper and see whether actually they have taken out the outliers, because sometimes they say there is a significant relationship, but because of two or three outliers. Okay, look at that. Completeness: always report means and standard deviations alongside R, so that the readers can understand how your data is spreaded. Special cases: if you get R -1 or +1, only when all points are exactly on a straight line, which we usually say cannot observe, because if you are measuring, you need to have some sort of a measurement error. If you get +1 or -1, that's something that you have to look at, whether there's an issue with your instruments or there's some sort of an issue with your methodology. So let's look at the car weight versus fuel consumption. The car weight is in pounds, and as the car weights increase, you can see the fuel consumption also increase, because it increase like this. Increasing values result in increasing values. Okay, so the car value, car type is given, weight is given, fuel is given. So let's look at again a positive association. Heavier cars use more fuel. Roughly linear relationship, a fairly strong relationship. R square is 0.95 here. So it's a fairly strong relationship. And I have shown you how to calculate the correlation coefficient here. Some xi and yi values, so you get the difference. And then you get a very strong positive linear association between car weight and fuel consumption. So that's where we end up looking at the charts, right? So far what we did was, in this 11A lecture, we talk about, now if I to explain what we did. So in this lecture, right? So far what we did was, we started with the basic idea of what is, look at this one. Yeah. So we have the research methods flow slides. So we talk about the descriptive statistics, outliers, and other charts of visuals, numerical visuals, because we would take data. If I talk about numbers, there is no meaning in that. But you collect your data and you draw your data, you take them into a chart, then only you start analyzing it. Always keep this habit with you when you are dealing with quantitative analysis, numerical data. Always draw the chart, always do the visualization, and then only see how and what are the things that you can do with it. Don't just blindly take the values and get the X bar, get the Q1, Q2, Q3. There's no point in it, because the values actually can be misleading unless otherwise you look at the distributions, the visuals of the data. Okay, that's the very first thing that you have to do. Collect your data, and obviously clean the data. Missing values and other things would be there. But when you do the visualization, only you will understand how they distribute and what are the things. Okay, so far, I want to get your opinion. Is it clear? So this is the first part of this lecture. Is it clear? So you get something out of it. Can you send me a message? Is it clear? Did you get some clear idea about how to approach your numerical analysis, your quantitative analysis? So first you take the data, you do your visualization. Okay. Right. Okay. So now let's go ahead with our next one, because next one links us with this descriptive idea to our distributions. So this one is a bit tricky because it talks about probability. So I go ahead and click on lecture 11B. This is the probability part of it. Okay. So I will start this, and it has some concepts. So if you don't get it right now, listen to me, but don't worry, you will get it. But it's very important to combine the descriptive statistics with the inferential statistics. So let's look at why it is so. So let me start presenting this. Okay. So here I'll be talking about basic probability as lecture 11B. We talked about descriptive, the numerical summaries and the visualization of data, how to look at the data. And now we are going to basic probability. What is probability? So we'll start with what is probability. So I'll talk about introduction and motivation. There are questions and answers. So written, solved equations, so solved questions. So we can go through them. Introduction and motivation, basic probability concepts, and conditional probability, and basic probability problems, and then counting rules and summary and applications. This would be very useful for you when you are doing your experimental design, and particularly understanding the patterns in your experimental rubric. Okay, so let's look at the world. So let's look at the world, and we need statistics to understand our large scale of data sets. So we need probability to come up with some questions. What is the probability of purchase intention versus actual purchase? So here we have a scenario: marketing manager analyzing survey about big screen TV purchase, survey of 1,000 households. Think about your own research, 1,000 households about intentions to purchase. So you have a big screen TV, 100,000 households, and you ask them their intention to purchase. Follow-up survey of after 12 months. So you wait 12 months and then you do the follow-up survey. And these are the thing, additional data collected. So look at your survey question. Key questions. What is the probability of purchase intentions versus actual purchase? So when you do your initial survey, people might say, okay, I'm interested in buying it. But then after 12 months, when you do it, then only you can compare what is the actual purchase. Then how do these variables relate to each other? How can we use this for marketing strategy? So that's the idea. So let's look at what we get. So when you look at this question, we have to come up with a basic understanding of probability. So what is probability? The probability is the numeric value representing the chance, likelihood, or the possibility that a particular event will occur. If you think about the probability, if you are, let's say, the probability of winning a lottery is very simple thing to come up as an example. But let's be more specific. Think about flipping of a coin. You take a coin and then you flip it. When you flip it, you have two possible outcomes. The first one is a head, the other one is a tail. There is no order in it, either head or tail. So these are the two outcomes. The property of a probability is that it's always positive, and impossible events will be 0, certain events will be 1. So when you are going for the survey questionnaires, when you are getting data, sometimes you get 0 responses for a particular thing, which means they might not actually exist in that the sample frame. So that's an impossible event. Sometimes people will always give, like if you go to a underprivileged area and then if you ask, are you satisfied with your income level, everybody would be giving you no, 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 because that would be a certain event. So there's no point in collecting that data because it doesn't give you some information about that particular place. So there are 3 types of probability. A priori probability based on prior knowledge. The idea of the past will give us some idea about the future. So that's a prior probability. Empirical probability is based on observed data. So if you go to for example, let me give you some idea. A priori probability would be if you are coming from different backgrounds, different universities, for example, you may agree with me that you have a prior understanding about University of Moratuwa because we have more males than females. So that's a priori probability. That's an idea. So if you do the math, you do the observation, you count the number of girls in a batch and count the number of boys in a batch, and then identify the probability. That's empirical probability. You observe and you create records, you get the data, and that's your empirical probability. Your subjective probability is the personal judgment. Now, in this discussion, I inherently had some subjective probability as well because I have personal judgment that at University of Moratuwa, the probability of observing a girl is lesser than the probability of observing a boy. That's personal judgment, but it might have changed. And also it's a priori probability, right? So you can think about different things about your research that falls into a priori, empirical, and subjective probability of observation. Now, probability of occurrence is simply the number of ways the event occurs divided by the total number of possible outcomes. Now, if you think about the coin example, number of ways that a coin would be shown after a flip will be two, head or tail, only two. So the total number of possible outcomes will be two. And out of these two, one would be your number of ways the event occurs, either head or tail. So 1 divided by 2, that is the probability of observing head or a tail. And in the case of a standard deck of cards, there are 26 reds, 26 black, and over 52. So it's a probability of 0.5, the same. Okay, let's go forward. The key definitions, there are events and sample space. So event, each possible outcome of a variable. So when we say each possible outcome of a variable, we factually say each possible outcome of a variable. You cannot remove any of the outcome. So if it is about a six-sided die, each possible outcome would be 1, 2, 3, 4, 5, 6. Okay. So each possible outcome of a variable is an event. So simple event described by a single characteristics, and joint event has two or more characteristics. Complement of A, which means anything, say the complement of head would be tail, anything other than what you are referring to, all events that are not part of it. Sample space, collection of all possible events. So the sample space, when you are referring to the head or tail example, the set containing all the things, that sample space. So when you are doing your PR exams or proposals or any defense, people might ask, what is your sample space? So what is your frame of reference? What is your population? So you need to have a proper idea of these things. In the sample space, you are putting all possible events. So if you are referring to, for example, a survey in Colombo district, for example, and this survey is about ethnicities. Okay. So your sample space in terms of ethnicity would include all the possible things like Sinhalese, Tamils, Muslims, Burgher, and also all the other ethnicities. I'm sorry, I forgot all of them, but you have to think about all of this, and then talk about your frame of reference, like the sample frame, and then maybe negate some of them or remove some of them based on your requirement. So that's your sample space. Okay, that's very important. And let's go forward. The purchase behavior for our previous example. Now you have an idea about your actually purchased and the total number. So the simple events: plan to purchase, actually purchase. Okay, plan to purchase and actually purchase. Joint event is they plan to purchase and they actually purchased. Now these are two different things. Plan to purchase, right? If you think about the cases of the plan to purchase, they have yes or no. They have 250 who plan to purchase and 750 who did not plan to purchase. Okay, so that's the simple event. actually purchased, they have 300 actually purchased and 700 who actually did not purchase. Okay. But in the case of joint event, plan to purchase and actually purchased, that is the two yeses. So they actually purchased it, yes, 200, and plan to purchase, yes, 200. So the intersection between plan to purchase here, plan to purchase and actually purchased, this 200 is the end logic. Okay, so when you are developing your contingency tables, these tables, make sure that you understand what you are talking about. If you collect your data, make sure you understand this joint events, simple events, what they actually mean. Because if you don't understand them, the numerical analysis actually it doesn't have a real meaning. It's wrong. So you have to understand what you are doing. Now let's go forward. So this is the sample space, the Venn diagram. By the way, Venn is the name, right? It doesn't mean like separation diagram. It's just Venn. Venn is the name of the person who did this. So you have A and you have B, A intersection B here, and and this is something that you know from your grade 11. So I will not dwell too much on it. This is grade 11, grade 10. Throughout grade 10 and 11, you do Venn diagrams. So you have some idea of what they are. But I'll talk about the standard notations a bit. The intersection is the overlapping part of this. Union is the total thing, and then complement is whatever that is not inside the set. And only A means A minus B. So think about this. You are doing a study about the, let's say, graduates or high income graduates, or then something like engineering graduates in B, and A would be working in Colombo. So working in Colombo, engineering graduates. So A intersection B means they are working in Colombo and they are engineering graduates, something like that. So only A means A minus B, which means this little rose color part excluding whatever related to B. So in that case, working in Colombo and nothing to do with engineering. So all the other people working in Colombo except engineering students. So that is engineering graduates. So that's very important. Only B is only engineering students, and we don't. They can be people who are they cannot be people from working in Colombo, because we are removing that part. At the end, you get like a Pac-Man kind of a thing. Okay. So symmetric difference and neither A or B. So look at these things and try to get. So plan to purchase, joint probability, marginal probability. You get these values. So you can please look at the lecture note. So it has everything. I'm not reading the numbers. I'll only talk about the concept. So let's go forward with the value. And now we get another interesting thing about independence. So you have two coins tossed, which gives an example head on first toss or tail on second toss. So this is like your hypothesis. So it's like the statement that you give. Give an example of simple event. So when you go to collect your sample from your, say, get an observation from your sample, you should have some hypothesis about what you are going to get. Example of a simple event. So if you go to collect data from underprivileged urban people who are suffering from flood in Colombo, you always have to have an idea about how they are, what they would look like, and what sort of an income level and place they are actually living in. So if you look at underprivileged urban population who are living in Colombo affected by flood, you don't go to Colombo 7 and then look at all those big houses, because they are not belong to either of them. So you have to have an idea about the simple event that you expect, right? And joint event and so and so. You can read about it. So there are some calculations. I'm not going to talk about the calculations. Please read the lecture note. And I'm actually interested in only the concept of this. So let's go forward. Yeah, there's something called mutually exclusive and collectively exhaustive. What do you mean by mutually exclusive, and collectively exhaustive. So you might find this in your research. So you are excluding, your examiners might be asking, what do you mean? How do you take this sample? So mutually exclusive means they are independent of each other. There is no, like in simple terms, like if you take a look at the gender neutrality out of the equation, the conventional way is you have females and males. They are mutually exclusive. There is no intersection in conventional terms. Collectively exhaustive means you get all those observations that are there. So collectively, they give the entire set. That is what it means. So if you look at the solution, mutually exclusive, yes, collectively exclusive, independent voters are. So read the question: registered voter, Republican or Democrat, car type, sedan, SUV, American, European, Asian, or none. They are not mutually exclusive because sedan can be American, but collectively exclusive, yes, because you have none here. When you add none here, because this one collectively comprise of cars, and when you say none also, it has all the things. So it's collectively exhaustive. Then here, residence, apartment or house, mutually exclusive, yes. Apartment and house are two different things. Collectively exclusive, no. Could have condo, mobile home, etc. Defective or not defective, yes. They are mutually exclusive because you can't be not defective and defective at the same time. They are collectively exhaustive, yes, because it comprises of all the product types, right? When you combine them together, they are collectively exclusive. They explain the entire thing as a single unit. Defective and not defective combined thing is the product itself, right? So it's collectively exhaustive. So that's the idea. Now let's go forward. So I will not dwell in these things. Let's go forward. Okay. So read about the questions and answers here. Then I will go to an interesting thing somewhere here in the conditional probability. So what do you mean by conditional probability? The conditional probability is the probability of an event given that the other event has occurred. So by definition, it says B has occurred, but we are dealing with sets. So basically what it means is, I will show you what it means. So let's look at this event A. So this yellow color is event A. And this blue color is event B. Okay, so this is event A and this is event B. So the conditional probability formula, PA given B, this one, PA given B. So we read it as PA given B, where B has occurred and A is the condition upon B. It is given as P, the probability of A intersection B divided by the probability of B. So when you look at this, so I told you that the blue color one is the B. So this is B, and the yellow color one is A. So this is A, right? So PA intersection B means simply this part. This is PA intersection B. And PB means this chunk. Okay. So by conditional probability, what it means is in the total set of outcomes of B, how much belongs to the intersection of A and B. So that's what it says. So the chunk of the entire probability of the space of B is here. And inside that, you have a part of A intersection B. So when you get this, the ratio, it simply means the number of items exist inside the set of B such that they have an intersection with A. So that is PA given B. And similarly, you get B given A. So in your sets, in your samples, you will find this. So sometimes you have to do a study about, as I said, underprivileged urban population living in Colombo who are affected by flood. So I have several conditions. So if you get a sample out of it, say how B given A, let's say B is the flooded, right? Who are flooded, and you get someone underprivileged in the flooded zone. So A given B flooded and underprivileged, right? So that is what it means. So you have to think about whether you actually represent what you really want to say in your samples, because the probability, the notation, the idea of conditional probability need to be understood when you are developing your research question. So events A and B are independent if and only if the conditional probability it does not make a difference to the actual probability. So subject of B subjected A does not do anything. In other words, now in B, occurred does not change the probability of A. And independence, whether we have an intersection and the probability gets multiplied. So I'm not going to talk about these things. So let's look at alternative to contingency table for visualizing probabilities. You can go for decision trees. And multiplication rule is simply multiplying the probability of conditional probability to get the intersection of probabilities. So we go forward, come to the other part. So please read this slide. And if you are a person who writes and understand things, take this slide, write this on a piece of paper, you will understand much better. Right, let's go forward towards the part that I want to explain more. Solutions are there. Okay, with and without replacements, probability. But I want to talk about something very interesting about Bayes theorem. So Bayes theorem is the idea, it's the central idea of actually what we do in research. Most of the time, what we do is this. We don't know the actual probability of the things happening in the real world, but we take a sample from it and try to identify that the idea of what we want to say. For example, we don't know all the cancer patients, but we know one set of cancer patients, and then try to get, if the cancer is there, what will be the other things. So that's what basically what we do in research most of the time. Okay, so understanding Bayes theorem would be very useful. So read this, try to do some calculations here. It will be, if you get some idea, it would be really good. Not necessarily important for our discussions, but that would be really useful. Okay, so I'm going to last part of the lecture. Counting. Counting is something that you have to understand when you are doing research. Counting means, let's say you have some possible outcomes. Say you are coming to the university. So I'll explain this in simple words. Okay. For mutually exclusive and collectively exclusive events, number of outcomes would be k to the power n. I'll explain what it is. So let me explain it. Right. So you have tossing of a coin, right? Mutually exclusive and collectively exclusive, because you can have head or tail. These are the only two outcomes that you can have, and they are independent. They don't have any interaction. Like getting a head doesn't mean that you get a tail next. So they are independent. So if you are going to toss the coin for 5 times, how many possible outcomes would be there? So if you have these spaces like this, you can fill in either H or tail, H or tail, H or tail, and H or tail, H or tail. So because of that, let's say I write H here, right? Then I can have all tails, HTT, okay? If I write H here and H here and H here, tail here, tail here, so I can write it like that as well. So if you think about all these possible outcomes, we can calculate it by number of outcomes. So we have possible 2 outcomes, and we need to fill in 5 spaces, like 5 trials, then 2 to the power 5 would give us all those possible all those possible numbers, all the possible number of outcomes. Okay, this is important when you are planning your research, when you are designing your research sampling. Think about the possible outcomes that you can sample from. And the number of outcomes, number of events differ from trial to trial. So I'll explain this in very simple way. So imagine that you are coming to the University of Moratuwa. So this is University of Moratuwa, and you are coming to the Moratuwa from Colombo. Say you are at Colombo Fort, right? You can choose to come by a taxi, right? Or you can come by bus, or you can come by train. So there are 3 possible ways for you to come from Colombo Fort to Moratuwa. Let's say that you have something to do at Ratmalana or Ratmalana Junction or Mount Lavinia, for example, and you have to get down from Mount Lavinia. And from Mount Lavinia, you have 2 possible ways to come to university again, using a taxi, using a bus, right? So basically, if you separate this decision, you have 3 possible choices and 2 possible choices here. If I ask you to write down how you came to the university, you can say, I took the taxi and took the taxi again. Sorry, this is taxi X, taxi X, taxi, taxi. And I can say, I took the taxi and then came by the bus. Or I can say, I took the bus and came by the bus again from Mount Lavinia, right? I took the bus and came by taxi from Mount Lavinia, took the train to Mount Lavinia and then came by the taxi, took the train to Mount Lavinia and then came by the bus. So these are the all possible things that I can get. So how many of them are 2, 4, 6, 8, 10, 12? So 1, 2, 3, 4, 5, 6. 6 possible pairs, right? So in order to calculate this, you can easily multiply 3 times 2. So all the possible outcomes can be calculated like that. That's what it says. Number of trials, you multiply by the possible number of trial independent one times the other ones, then you can get the all possible outcomes. So this is very, very important, because when I look at the research, when I see research designs, people have not considered these possibilities. So you have to take a matrix, you have to develop this table and identify all those possible events that you can observe in your data. And then you take your sample, then you have to understand your sampling frame to capture all the possibilities and to actually look at your scope about sampling, about what you really want to say. So that is about how you decide the number of events when trial to trial is different. Now, next one is factorial. I'm not going to delve in too much in the factorial part, because I think this one would be useful if you are doing research mostly in quantitative sides. But other 2 are important when you are deciding your sample and you're designing your work. So for the counting, like NPR and NCR are there. So read about it and you'll understand what it means. Permutations and combinations. So we'll go for the questions and the answers are there. So when you read it, you will understand it better, right? What permutations and what combinations are. So the summary, we talk about basic probability, conditional probability, Bayes theorem slightly, and then talk about counting rules. So we have some examples here. And why did I do this? Because I talked about last time when we deal with the samples and populations. You have a population, right? This is your population, right? And you are doing a sample. You take a sample out of it. So this is your sample. When you do that, right? This is your sample. When you do that, you can have multiple ways of choice. Okay, we have many ways to choose from this. So if I explain it in very simple way, I will show you this in Excel, just to show you the concept of how important it is to understand your sampling. So let me show you. Let me show you in Excel. So let me open up an Excel, right? And let's increase the size. Okay. I hope you can see my screen, the Excel, hopefully, right? So imagine that you have number of possible outcomes in your population. So this is population. So I will take 12, 43, 26, 31, 67, 32 again, 18, 23, 64. So this is your population. Okay, this is your population. Now, this is your population. Now, because of your research, okay, because of you are going to sample from this, you will be sampling only 4 out of this. So how many actually capital N, even though it's impossible to calculate, we have nine elements in our population. So you are only taking 4 out of it. Now think about all the possible ways in which you can get values from this. So 9 out of 4. So we can calculate 9 factorial. So we have combinations. So we say combinations, combinatrix. Number is 9 and number chosen is 4. So you have 126 possible ways to get 4 items out of this 9. Okay. You can't do this. So what you do is you basically select a sample. Okay. That's what you do. Now let's look at when you do what will happen. So I'm going to select 4 from this. Okay. I'm going to select 4 from this. So I'll say choose this value. So let's say that it's going to work. So it will be giving me, I'll just write it in a simple way. So I'm going to pick, so this is my sample. These are possible samples. I'm going to select possible samples. So 4 samples. So this is one of my samples. This is another one of my samples, right? And this would be another one of my sample. Okay. And this one would be another one of my sample, right? And this one would be another one of my sample. Very simple. Right. Now let's look at what is happening. Now, the population mean, or the average mean, average of the population is going to be the average of this. Okay, 35.1. Now, these are my X bars. So these are my sample means. My means I'm not doing all these things, okay? I can only do one out of it. So this is my sample mean, sample average. This is my sample average for this sample, and this is my sample average for this. So these are my sample averages. Now, if you look at this, okay, depending on your sample, the average, or in simple terms, the numerical summary that you get changes. In the population, you have 35.1. So in numerical analysis, in quantitative analysis, what we try to do is when you do this inference, or when you do this thing, and when you want to generalize it from here, from the sample to the population mean, the inferential part, that is where we look at the possibilities like chi-square, z-score, or t-value, and all these things are there to make sure that we shoot properly. We shoot here to this value with a certain confidence interval. So we are more certain about the population. Of course, there are things like the the law of large numbers, central limit theorem, and many other things which we will discuss in the next lecture. So why probability is important? It's because it dictates how you take samples from your population, and based on your sampling mechanism, the way that you infer about the population will be affected. And you need to understand how accurately you take your samples from your population. All right. So we'll talk about these calculations and things about that in the next lecture, so that you get a better understanding, because there are some calculations I need to do with you. Right. That being said, so what I'm going to do now is I'm going to give you uh, an exercise, a group activity. I'll put this in the Moodle. So what you have to do is to find, I'll put some publicly available data sets in the Moodle. And what you need to do is develop numerical summaries of it, like standard deviation, mean, median, and the box plot. So I don't care how you do it. You can use Excel, you can use Python, you can use R if you are familiar with it. I'll give you different data sets. So you develop those things in the group activity, and then you need to put some, I'll give you the assignment briefing. You have to put a report on what you have found. So I'll give you various variables, and I'll ask you what you feel about it. So you can pick the data set and do your preliminary investigation, the exploratory data analytics part, and give us the results. Okay. So that's one simple task that you have to do. It's a group activity. I'm not going to be harsh on that. You can decide who is going to be your partners, and better if it is only like four or three members per team, so you have better, better interaction with your team members, and you contribute. So look at visit the Moodle. Today the Moodle would be a bit shaky. There's some maintenance going on, so I will upload the data sets, the links to the thing, and the assignment briefing in the Moodle. Visit it, and no harsh deadline, probably by next week or week afterwards, or maybe by next Friday, hopefully, because I'll be meeting you next Monday and then Friday. So 4 or 5 lectures would be done, and then the last one would be on the next Monday. So would be much better if we can have it by maybe mid Wednesday next week, so we have some freedom to discuss about the results and interpretations of it. But when we meet for for the Friday lecture next week, so think about that as well. I'll set the deadline, not a harsh deadline, but just do it in groups, and then upload. We'll discuss about the results in the class, right? So there would be something interesting coming on in the next lecture. So please bring your notebooks to the lecture. Like this will be online anyway, but better if you engage with the lecture, so you get an idea about the quantitative analysis in detail, because there is no point in learning about quantitative analysis without actually doing it. There is no point. So we'll look at it, all right, in next lecture. So I will conclude today's lecture here. And if you have any question or anything, you can ask. And I'd appreciate if you can give a comment on how you felt about the lecture, whether you got it, whether you enjoyed the lecture. That would be really useful for me to understand how you understand it, and how we can proceed. Okay. If you don't have anything to say or you can leave. No problem. Have a nice weekend.